Hello students, continuing in the chapter of gravitation, in today's lecture let us discuss satellite motion and the Kepler's laws of planetary motion. Let us talk about satellite motion. Consider our Earth. Let us suppose the mass of the Earth is capital M. So as we have discussed in earlier lecture, the entire mass of the Earth can be assumed to be concentrated at its center. The radius of the Earth is capital R, and assume that a satellite is rotating at an altitude h. This is, you can say, a satellite rotating in its circular orbit. For the sake of simplicity, right now we are talking about circular orbit only. Let us suppose the mass of the satellite is m. Maybe right now we are talking about a satellite which is rotating around the Earth. This kind of satellite may be an artificial satellite as we happen to launch, or maybe there can be a natural satellite, for example the moon, which is rotating. Assume that this rotation is in circular orbit. So for that matter you can say that the radius of the circular orbit is small r, and this small r can be written as capital R plus this altitude. The height of the satellite from the surface of the Earth, which you call altitude, is a small h, and the radius of circular orbit which you have, this is small r. Now you see, first of all try to understand that why an object is rotating in a circular path. Recalling our earlier discussions of circular motion, we have always said that for a body to move in a circular path, it should satisfy two conditions. It should have a velocity, and it should always have a perpendicular force experiencing. For example, here the satellite has an orbital speed VO, as you have indicated, and a constant gravitational force is acting on the satellite due to this Earth, and this force is all the time acting towards the center. This is the gravitational force. Let's suppose after some time the position of the satellite is here. The velocity will be tangential to the circular path, but the force of gravitation will all the time acting towards the center, and that force will always be perpendicular to the instantaneous velocity of the satellite. Now there are several aspects involved with this satellite motion. You are expected to comment on the orbital speed, also on the time period this satellite will be taking, what is the energy involved, what is the kind of trajectory it has got. All these things you have to discuss related to satellite motion, whether it is artificial satellite or natural satellite. You have to discuss all these things. Now you can see that whatever is the plane of rotation of the satellite, the center of that circular path of the satellite and the center of the Earth must coincide. You can see here, you have the liberty, the satellite can rotate in, say, equatorial plane. Let us suppose this satellite is not rotating this way, rather it is rotating this way in the plane of equator, then that will be essential condition for a satellite to be a geostationary satellite. If let us suppose it is a polar satellite, then it will be rotating somewhere like this. But whatever may be the situation, you will find that the center of the circular orbit of the satellite and the center of the earth, that will be coinciding all the time. It cannot happen that a satellite is rotating somewhere here. This kind of situation cannot happen. You understand? So first thing you should remember, that whatever is the plane of rotation of that satellite, the center of the orbit must coincide with the center of the earth. Now first let us talk about the orbital speed of the satellite. Let us talk about the orbital speed. We are denoting it by VO. Now as we said that the orbit is circular, and for circular motion the only condition we had, that is net force towards the center must be equal to mv square by r. This was the equation we have written whenever a body is under circular motion. This net force towards the center is any of the real forces. Right now it is the gravitational force. Earlier it used to be tension or say normal force. Any other force was acting towards the center, and that was responsible for the circular motion. This force was given another name which you called centripetal force. So here you can say gravitational force is playing the role of the centripetal force. Let me remind you again that centripetal force was not a new kind of force. Rather, all those real forces which were acting towards the center, they were given the name centripetal. And mathematically that must be equal to mv square by r. M is the mass of the object which is rotating. For example, here the mass of the satellite. V is the orbital speed, and r is the radius on which this satellite is rotating. Now, right now for this net force towards the center, we can write the gravitational force, that is capital G, capital M, small m upon r square. Now what is this capital M? Capital M is the mass of the earth, capital G is universal gravitational constant, and this is the mass of the satellite. R is the radius, and that should be equated to mv square by r. You understand? So here this small m cancels out, and this v was essentially the orbital speed, so I am writing it VO, and if you equate it, then you will find that the expression for orbital speed will be equal to under root capital G m by small r. This is the expression for the orbital speed of a satellite. Now there are several things to be learned here, that this expression of orbital speed is not involving small m. You can see in this expression that small m, which was mass of satellite, this is small m which was the mass of satellite, it is not coming into the picture of orbital speed. So whenever we are throwing artificial satellites in their orbits, whatever mass of the satellite we have taken, that becomes immaterial, so long as the rotation of this thing is concerned, and it is just dependent on the central mass. For example, central mass here is capital M, that is the mass of the earth, and the orbit in which you are placing it. If you see the expression, r is in denominator. That means if a satellite is very close to the surface of the earth, the value of a small r will be very small and the orbital speed will be very large. But in case r is increasing, in case satellite is orbiting at a larger altitude, then its linear speed becomes less. This is first thing you should keep in your mind, that if a satellite is rotating very close to the surface of the earth, its linear speed will be very large. It is placed at higher altitude, then its speed will be very less. If you take practical cases, then in the beginning, whatever satellites we had thrown, say Aryabhat, Bhaskar, they were just on 20 kilometer altitude, they were rotating around the surface of the earth, just above the atmosphere, because they were just the test satellites. So they were assumed to be rotating very close to the surface of the earth, and they had the maximum speed of the satellites possible. If you substitute the values small r as capital R, then you will find it comes out approximately 8 km per second. That means a satellite, if it is rotating very close to the surface of the earth, then it has maximum speed that of approximately 8 km per second. If you are moving on higher altitude, say if you talk about polar satellites, they are rotating at around altitude of 750 km, then their speed will be less than 8 km per second. If you are talking about geostationary satellites, which are almost at an altitude of 36,000 km, that means the 6 times the radius of the earth, their speed is very small, much less than 8 km per second, approximately around 3 km per second. You understand? So you should keep this thing in mind, that a satellite which is rotating very close to the surface of the earth, it will have a very large speed. As the satellite is placed on higher altitudes, its linear speed becomes less. Now you can correlate this orbital speed with the escape speed as well. If you remember, in the last lecture we had talked about escape speed, and we had also said that escape speed is not a quantity which is constant. For example, you made the derivation of escape speed as under root 2 gm upon small r. This was the expression for escape speed you had. And we had said that on the surface of the earth itself, it has variations because the acceleration due to gravity is varying, and in case the satellite is on higher altitude, then this expression of small r is changing. On the surface of the earth, this small r was replaced by capital R, and its value came out to be approximately 11.2 km per second. But right now we are talking about the escape speed of a rotating satellite. It is already rotating. Keep at the back of your mind that escape speed was related to zero energy. The moment you are making the energy of a satellite zero, it will escape. When we made the derivation, that time the object was stationary on the surface of the earth, its energy was very low, and that's why you had to give very larger speed. But when the satellite is already rotating, then you see it has some potential energy, some kinetic energy is also present. Then in that case you will find that the escape speed will become less. You understand? Because already its energy is higher and you have to make it to zero, so you require lesser effort. But right now, if you correlate these two, if you correlate the orbital speed of a satellite with the escape speed of the satellite, then you can see it's only the factor of root 2 which is extra in the expression of escape speed of a satellite. So in case you correlate these two, then you get a very important relation, that escape speed, this is equal to root 2 times the orbital speed. You understand? Whatever is the orbital speed of a satellite, if you multiply it by a factor root 2 is approximately 1.414. So in other words, you can say when the orbital speed of a satellite is increased by 41.4%, then that satellite will have the tendency to escape. This is a very important relation based on which we ask several questions. Now, with the concept of this orbital speed, you may be interested in finding out what is the time period of a satellite in its circular orbit. So let us talk about the time period of a satellite. If you talk about the time period of a satellite, Then you can start off from your same basic equation, that net force towards the center, that was gmm by r square. This was equal to mv square by r. And if you are interested in time period, then this v can be replaced by omega r as well. Omega was the angular speed, if you remember. So this can be written as m omega square r. You understand? This can be written like that also. And in case omega is replaced by the time period, then you can further write it gmm upon r square is equal to m into 2 pi by capital T whole squared into small r. You understand? This angular speed omega has been replaced by 2 pi by T. T is the time period in which you are interested. And what is this small r? This small r is the radius of the circular orbit. This is the complete distance from the center of the earth. It is not as such the altitude. Rather, you have already written the relation that the radius of the orbit is related to altitude, like the radius of the earth plus altitude. Now if you simplify this thing, you will find again the mass is cancelling out. This time period that will be going here, t square. Here you can say this is 4 pi square. This becomes r cube upon gm. You understand? This is the expression of time period you are getting. In case you remove this square, then you will have to apply a square root here, and this becomes the time period of a satellite. Now you can make a lot of manipulations in this particular expression. For example, this 4 pi r square, in case it comes out of the square root sign, it becomes 2 pi. For this small r, you can make this substitution capital R plus altitude. You understand? And this capital GM, frequently you can replace it by gr square, where you should remember that this small g is the acceleration due to gravity on the surface of the earth. Now again, with this expression of time period of a satellite, you have several things to learn. You can see this capital R is constant, this capital R is constant, this small g is also a constant. And time period is essentially related to the altitude of the satellite. If satellite has larger altitude, say geostationary satellite is at 36,000 kilometers from the surface of the earth, that is the largest altitude we generally think of satellites, then its time period will be very large. It is directly related to altitude. But in case a satellite is very close to the surface of the earth, then the value of h is very small. Or maybe if you make h equals to 0, then you will find that the time period of the satellite comes out to be 2 pi under root r by g. And that you had already seen that had the value 84.6 minutes. So in case a satellite is rotating very close to the surface of the earth, which had a speed of 8 km per second, that will have the time period of rotation to be around 84.6 minutes. But in case you are going above, say, geostationary satellites, then the requirement becomes that geostationary satellite has same time period as the rotation of the earth, and that is 24 hours. So in case you are increasing this value, 24 hours means 86400 second. In case you are putting 86400 second and then you calculate the value of h, that gives you the value h is equal to 36,000 kilometer, and that becomes necessary for placing a satellite like a geostationary satellite. Understand? How did we arrive at this value of 36,000 kilometer for a geostationary satellite or geosynchronous satellite? Geosynchronous satellite had the requirement that it should have the same time period of rotation as that of the rotation of the earth, and that is 24 hours, and that made it essential that the value of h should become 36,000 kilometer. And that is the reason all these geostationary satellites are placed in equatorial plane at an altitude of 36,000 kilometer. You understand? If you talk about polar satellites, we had said that they had approximately, you can say, altitude of 750 kilometer. So if the value of 750 kilometer is put here, then that decides what will be the time period of the polar satellites which are used here for remote sensing and all. If you substitute the value of around 750 kilometer here, then you will find this time period comes out to be approximately 110 minutes. So the polar satellites, they will be rotating around the earth in only 110 minutes, or maybe if you see their position on the India, then approximately they take 4 minutes to cross over India. They are moving at larger speed, not at the same speed as that of the geostationary satellites. You understand? So these calculations of time period and altitude can be seen with the help of this expression. Now if you concentrate here on this expression of time period in terms of the radius of the circular orbit, then you see that time period is proportional to 3.5 power of radius. This is a very important relation we will be coming across later when we talk about Kepler's laws of planetary motion. But right now, with the help of Newton's law, you can see that time period, this is becoming proportional to r raised to the power 3 by 2. These are two things which is very much important so long as this time period of satellite is concerned. You understand? Now let us talk about the energy of a satellite. If you are talking about energy of a satellite, essentially we mean the mechanical energy, that is the kinetic energy and potential energy. Now if you talk about kinetic energy, then you have seen that the expression half mv square is always there. For kinetic energy, no other variations. So this will be written as half mv square. This v is the orbital speed, and you had seen that the basic equation for a satellite motion was gmm by r square was equal to mv square by r. So if you employ this expression for mv square here, you can say that this r cancels out this one power and mv square becomes gmm by r. So if you are substituting this expression here, then you can say that the kinetic energy can be written as gmm upon twice of r. This is the expression of kinetic energy of a satellite which is rotating around the earth, or maybe for that matter about any central object. So this is the expression of kinetic energy in terms of the universal gravitational constant, the mass of the central object and the mass of the satellite. So here you should remember that kinetic energy is dependent on the mass of the satellite. However, you saw that the time period or orbital speed, that was independent of the mass of the satellite, but kinetic energy involves the mass of the satellite. Now if you talk about potential energy of the satellite, then you see it is something like this entire mass of the earth is concentrated at its center, and this small m is placed here, and the separation between these two is small r. Then you had seen the potential energy expression, gravitational potential energy was given as minus g capital M small m upon small r. This was the expression for potential energy of a satellite. And if you add these two, then it becomes the total energy of the satellite. So total energy, in case you write down, then it becomes sum of the kinetic energy and potential energy. Sum of the kinetic energy and potential energy. If you add these two, then it will become minus g capital M small m upon twice of small r. You understand? If you add these two, you will be getting this expression. Now you see there are several things to be learned here. First of all, we may ask you like, comparison of the energy of two satellites. They are in different orbits. One orbit is of a smaller radius, another orbit is of larger radius. Then you will see that as the radius is increasing, here the denominator will be increasing. In that case, the kinetic energy of the satellite will decrease if it is placed on higher orbits. You understand? If the satellite is rotating at higher altitude, its kinetic energy is less. Kinetic energy is maximum only for those satellites which are rotating very close to the surface. But if you talk about potential energy, then you see the value is in negative. You see this? This is negative sign. The potential energy is negative quantity as being shown by this expression. That means that satellite which is very close to the surface of the earth, it will have maximum possible negative potential energy. And if it is possible that a satellite has been placed at infinite distance, then its potential energy will be zero. That means if you are going on upper side, then the potential energy of the satellite which is on higher altitude, that is more. You understand? As the value of small r is increasing, if the satellite is placed on higher orbits, then its potential energy is increasing. And if I ask you to comment on the total energy of the satellite which is orbiting, then again you can see this is negative energy, total energy is negative, and the radius is in denominator. So in case you are talking about higher altitude, then again you can see that total energy will be increasing as it happened for potential energy. You understand? So the summary here for energy is that if you are moving on a higher side for a satellite, kinetic energy decreases, but potential energy and total energy increases if the satellite is rotating on higher and higher altitude. You understand? Now this total energy which you see, that is a negative quantity. That means your satellite is bonded to the central object. In case somebody asks you what is the meaning of this negative total energy, so negative total energy simply means that this satellite is bonded to the central object. It is something like, you can compare it with the motion of electron inside a nucleus. You might have read that the energy of an electron in its first orbit of hydrogen atom is around minus 13.6 electron volt. Now what was the meaning of that minus there? Minus meant that the electron is bonded to the nucleus. The moment you were making that energy to be zero, then you were saying that that electron has left that atom, that has become free, that was called ionization energy and so on. So here also you can think of a term called binding energy. You understand? You can think of a term called binding energy, and that binding energy is basically negative of this total energy. Binding energy is essentially the total energy value, but in positive sense. Let's suppose this negative value is minus 10. Minus 10 joule, if it is total energy, that means the binding energy is the positive aspect of that, that is plus 10 joule. This is the binding energy. So binding energy and total energy, they are interrelated. Binding energy simply means what is that much energy which is binding that satellite to the central object. Now if you compare these two and these two, then you will find there is some relation between all these three types of energy which you have written. You can see that this total energy which you have written, that is just the negative of the total kinetic energy. You can see here it is gmm upon 2r, but the total energy expression is minus gmm by 2r. That means total energy is negative of kinetic energy. This is the first thing you should remember. And second thing, you can see, if you compare potential energy with the total energy, then you will find that when total energy expression is multiplied to 2, if you multiply this expression to 2, then this will become the expression of potential energy. So you can say potential energy is twice of total energy. This is another expression you should remember. We may ask you a question that in case potential energy of a satellite is x, then what is the kinetic energy of that satellite? Then you can say if potential energy is x, then total energy is x by 2, isn't it? If potential energy is x, then what is total energy? Total energy is x by 2. And in case total energy is x by 2, then kinetic energy is minus x by 2. So these are the kind of interrelation which can be demanded. And remember that this expression will be coming at all those places where force is proportional to 1 by r square. For example, this kind of similar expression you will be arriving at when you are dealing with atoms. If you talk about the total energy of electron which is revolving around it, there also you happen to come across a term like this. You understand? So these are the few points you should keep in mind so long as the energy of a satellite is concerned. Now let us talk about some of the concepts which are related to the energy, and essentially this energy and this orbital speed, they decide the kind of trajectory all these satellites will be having around them. Let us talk about the trajectory of a satellite. Consider the Earth. Let us suppose a satellite is orbiting it in a circular path as we have derived. Let's suppose this satellite is having its speed to be equal to orbital speed. Your orbital speed was under root gm by r. You see that in whatever orbit this satellite is, in case it is maintaining an orbital speed like under root gm by r, then its path will be circular, as you can see here. This is rotating in a circular path. It will be maintaining a circular path. And you have already seen that in that case its energy will be negative. Now in case its speed increases, you have already seen that the escape speed of a satellite is under root 2 gm by r. Now somehow let us suppose you are increasing the speed so that this satellite acquires a speed equal to the escape speed. Then you will find that its energy will be 0 and it will make a parabolic escape. You understand? In case the same satellite which is rotating in circular orbit, somehow you have increased its speed to this much extent, like its speed has been increased root 2 times, or you can say 41.4% increase of the speed has taken place, then you will find that this satellite will make a parabolic escape like this. It will no more be rotating around the Earth. But in case, say, you are having a speed larger than this, if this satellite is having a speed greater than the escape speed, then you will find that it will again escape, and this escape will be hyperbolic. Much easier to escape. You understand? There are three main things you should keep in mind, that when the speed is equal to orbital speed, energy is negative here, it is making a circular trajectory. If you increase the speed and make it equal to escape speed, almost root 2 times, then it will make a parabolic escape. In case the speed is more than the escape speed, again it will escape, but escape will be hyperbolic. Now you see, here the energy is 0. In parabolic escape the energy is 0. If the speed is in between these two, then also it will be making motion around the earth, but that motion will be elliptical. Understand? That motion will be elliptical, and in that case this distance will be less and other side of the distance will be more. And if it is having a speed less than this circular speed, then also it will have an elliptical path, but in that case this distance will be more and this side distance will be less. These are the 5 possible trajectory. If you summarize here, in case it is lesser than circular speed motion, then it is a parabolic trajectory. In case it is slightly more than the orbital speed, then also it is elliptical. If it is equal to the escape speed, then the motion will be parabolic, it will escape, and in case it is higher than that, then the escape will be hyperbolic. So long as the speed equals to escape speed is concerned, the energy will be 0, but below that speed the energy will be negative, and above that the energy will be positive. These are the things which are related to trajectory and the speed in that trajectory and the concerned energy with that. You understand? Now let us talk about a concept which you call weightlessness.